Hello, everyone. Welcome to another calculus video, another video on integration by parts. So this function may seem kind of familiar. This is the one we integrated by parts in the last video. So let's step it up a notch. How about instead of an x, let's say we actually have x squared and we want to integrate this by parts. So if you watched the last video recently, you might remember that there was a bit of a strategy in choosing u and choosing dv strategically so that this thing turns into something that we can eventually take the integral of. So just as a quick refresher, we have one function here, one function there. We want to pick u to be the function that gets simpler the more we take the derivative of it. So it's a choice between x squared and a choice between sine of x. So if we take the derivative of x squared, we get 2x. If we take the derivative of 2x, we get 2. If we take the derivative of 2, we just get 0, basically the absence of value. We'll do the same thing for sine of x. The derivative of sine of x is cosine of x. Derivative of cosine of x is negative sine of x. And then derivative of that gets us negative cosine of x. And then the derivative of negative cosine of x is essentially negative sine of x, which ends up just being sine of x. So as you can see, this one does not get any simpler the more we take the derivative of. It stays fairly consistent. It just switches between sines and cosines and eventually changes from positive to negative every few turns. But if we were to look at this other function we have, x squared, this one, it's easy to tell that the derivative does get simpler. We get a simpler function every time we take the derivative. So that being said, this definitely should be u. U should always be the function that gets simpler when you take the derivative. This is u. So by default, this must be dv then. So we have a u, we have a dv. Looks like just looking at the formula, we're also going to need a v. We're also going to need a du. Both of those things are relatively easy to find. We'll start with du. We have u as x squared. So du is going to be part of the derivative of x squared. If we take the derivative of u, we get du dx. And of course, that ends up being 2x. But because integrals typically don't have an entire derivative on the inside, they only involve one of these two differentials. For example, this integral doesn't have a du, it only has a dx. And the reason for that is we multiply both sides by the differential not being used by this particular variable. So we end up just getting du equals 2x dx. This is something that we're going to be using in our formula. If you look over here, we definitely do need du, and we have found that already. Du is just 2x dx. The one last thing we need, though, that we don't have yet is v. We don't have a v, but we do have a dv. dv is just sine of x, and we want to make sure we have the differential there as well. So how do we go from dv to v? Well, let's go from u to du. We know we just took the derivative. We start at u and we want to go to du. We have to take the derivative. But what if we went backwards? What if we had du and we wanted to find du? Well, then we take the antiderivative naturally, do the opposite of taking the derivative. So the same thing applies right here with dv. We want to take the antiderivative of dv, which gets us v. So the antiderivative of sine of x is negative cosine of x. All right, so we've already done most of the heavy lifting. We have strategically picked our u and our dv. We have found those additional values that we didn't have right away. We didn't have dv. No, we didn't have v and we didn't have du. We found both of those with relative ease. So the next step is just plugging in everything as they appear. So we already have this first part down. No sense in copying that again, but that's going to be equal to u times v. U is x squared. V is negative cosine of x. And then we have minus the integral of v times du. v is negative cosine of x, and then du is 2x dx. So in the last one, when we got to this very last part, we had something that we could take the antiderivative of right away. We just had negative cosine. But this time we have an x in it. And even if we were to simplify things a little bit, even if we were to combine these, make them both positive, and then move this 2 out front, we would still have x times cosine of x, something that does not integrate easily. So we know we have to do yet another integration by parts. We have to do another iteration of this technique. But before we continue, let's just tidy this up a little bit, maybe simplify where possible. All right, and then after that, I'm gonna make this positive 2 times whatever is left on the inside of the integral. So that would be times cosine of x times x, but I wanna put the x first. All right, so we can tell that we have to do integration by parts again, but I just want to note that this is already much simpler than what we started with, right? We want to do one more iteration of integration by parts and see if we can simplify this yet again, and then take the antiderivative using just the elementary techniques, hopefully the ones we learned just in Calc 1. Hopefully it won't take anything more technical than that. So let's rewrite this exactly the way it appears, the first term. Plus 2. And then what I like to do is I like to make a box. And the reason why I like to make a box is because we're going to rewrite this entire integral. And I'm going to rewrite it and put that in the bigger box. So we have to use integration by parts yet again. So by the same logic for which we used to pick a u and dv at the beginning, it's going to apply here as well. U gets, this x gets simpler the more we take the derivative. So naturally that must be u. This must be dv. So then our integral becomes this. We're going to apply integration by parts one more time. We're going to have u times v. And then for this one, we have dv is cosine of x, and the antiderivative of cosine is sine. So if dv is cosine of x, v is going to be the sine of x. And then we have minus the integral of v times du. V is still going to be the sine of x from before, just used that. And then we just have to finish it off with du. Du is going to be the derivative of x, which is just going to be 1 dx. So dx is going to be the derivative. All right. So let's kind of bring everything together like so. Remove the box and replace it with parentheses. So we were able to simplify it into something that does integrate pretty easily. But let's clean up what we have here for a second. Let's clean up, combine like terms, and distribute where possible. And then we're going to distribute this 2 to the second term as well. We're going to make this minus 2 times the integral of sine of x dx. And I'm going to erase some of the stuff we don't need anymore. Don't really need this intermediate step right here. So let's integrate this. We have a negative out front. So what we're basically trying to integrate is if we ignore this 2, we have negative sine of x, which means the antiderivative of that has to be positive cosine. Positive 2 cosine, putting the 2 back in there. So it turns it positive again. We get positive 2 times cosine of x, because that's the antiderivative of negative sine, plus c. As you can see, we have finished. We have all 3 terms, not a single integral in sight. So we're finished. This is how we apply integration by parts twice to solve a particularly tricky problem like this one.